Hello and welcome to week 3. This week we are covering hierarchical and stepwise regression, and that just means that we're going to be adding predictors in certain order to understand the incremental variance explained by each additional one. And so we'll be doing that mostly, and then at the end we'll be doing some checking of assumptions. So there are some assumptions in regression that we need to keep in mind in order to get the most accurate results at the end. So those are the two topics that we'll be covering this week. Before we add new content to our knowledge base, let's first go over what we've learned in the previous couple of weeks. So the first question is pretty basic. We want to know what these R's mean. So we have the small r's and then we have the large R's. And the small r's give us an association between two variables, just in the bivariate case. So the little r tells us the strength of an association between an x and a y variable. And recall that the absolute value tells us the strength of the relationship, and then the sign tells us the direction. If we square that number, we get the r squared, little r squared, which is an effect size, and it gives us the proportion of variance that is explained in y by x and vice versa. Okay, so it gives us that proportion of variance explained. The large r's are for the multivariate case, where we have two or more predictors in explaining variance in a DV of interest. And so the large R is the strength of the association between the DV and an optimally weighted combination of predictors. And if we square that, we have the proportion of variance explained in the DV by an optimally weighted combination of predictors. And both R squareds are indicators of an effect size. The proportion of variance explained specifically. The second one, what does the B weight represent and the beta weight? Well, what they both have in common is that they're a measure of the slope of the best fitting line. So for the B weight, that's the unstandardized slope, or the raw unit. So as we move 1 unit increase in a predictor, what do we expect the DV to do? How do we expect it to change? So again, if the slope is negative, if the B weight is negative or the beta weight, that means that we have a negative association there, negative slope. And if it's positive, then we have a positive. And for the beta weight, it's very similar, except that it's in the standardized unit. So as we increase the predictor by 1 standard deviation, what change do we expect in the DV? So that's what those two things represent. If they are significant, that means that, and they both will be significant or they both will not be significant. One can't be significant without the other. And that just means that we expect a significant change in the DV based on that 1 unit increase in the predictor. What is the formula for B in the one predictor case? Recall that that is the R, so the little r, and that would be multiplied by the fraction of the standard deviation of y over the standard deviation of x. So that's a quick way to get the B weight. What is the formula for the beta in the multiple predictor case, specifically in the 2 predictor case? I will never ask you to think about more than 2 predictors when we're thinking of B weights. So the formula for that, recall, is the correlation between the DV and the first predictor. So remember that was RY1, or just R1. And then we're going to subtract off of that the product of the of 2 things. Remember the correlation between Y and predictor 2, and then the correlation between the 2 predictors. Remember that was R12. And then the denominator of that, so we're going to divide that by 1 minus R12 squared. And that's going to be on the denominator. So we're going to touch on this formula again in this lecture, and the goal is for us to understand what happens when that R12 increases. What happens to the whole formula? What happens to beta? What is the purpose of regression? Well, the purpose of simple regression, remember in the two variable case or the bivariate case, is we want to know what will happen to the DV based on the knowledge of a predictor variable's value. Okay, so what is the expected, more specifically, what is the expected value of a DV when we have knowledge of the value of a predictor variable? And the purpose of multiple regression, again, 2 or more predictors, is we want to understand the expected value of the dependent variable based on knowledge of an optimally weighted combination of those predictors. Okay, so you can kind of see a pattern here in the answers, right? So the purpose of regression, and overall, in the bigger scheme of things, the purpose of regression is prediction. Always prediction. Compare ANOVA and regression. So ANOVA technique and regression have some similarities, and there will always be an ANOVA table in ANOVA analysis and in regression analysis, so that's kind of interesting. The ANOVA table is helpful for both. But the methods themselves, you'd use them differently. So ANOVAs are great for categorical predictors. When you're looking at mean differences across different groups on a DV, then a one-way ANOVA is appropriate. Regression, it also does that well, but you'd have to do some coding for that if there are if there are more than 2 groups. So we'll cover that later in this course. Regression handles nonlinearity very well. So if we're expecting a curvilinear relationship, I think we'll cover that next week. ANOVA can't handle that. Regression can handle categorical predictors and continuous predictors in the same analysis. So if you were looking at different departments, wanting to predict differences between people from different departments and understanding that, and plus you would want to understand their conscientiousness levels or other kinds of continuous predictors, individual difference kinds of variables, you could put both of those in the same equation with some coding for the categorical variable, like what department the person is from, and you would be able to use regression for that, but you couldn't use ANOVA. Maybe you could use an ANCOVA, but I think regression is probably the better way to go. Other differences between them. Regression handles dichotomous DV, and ANOVA doesn't. So when we have a dichotomous DV like a person's guilt or innocence, or the probability of contracting some kind of disease or having some kind of issue, those kinds of dichotomous DVs or outcomes are handled with regression much better than ANOVA. Remember the the cell sizes, remember the n's for the different cells in ANOVA, they have to be equal or should be equal. For regression, that's not as big a deal. So overall, regression is more flexible technique and can handle various kinds of predictors much better. Oh, and one more thing. Regression also can partition variance much better than ANOVA can. We can see unique variance accounted for by certain predictors much better, and also regression accounts for correlations among the different predictors. So it's just a much better technique overall for the most part. It depends on what analysis you're doing. ANOVA can still be good. One ways I think are used probably the most when we just have like 4 different departments, for example, and we're trying to figure out if the sales differed across those 4 departments. That would be a one-way ANOVA. That would be an easy one where we wouldn't want to use regression probably for that. But more on that to come. So just thinking through these things, you'll learn more as we progress about when we would use different analyses to answer different kinds of questions. Next, what does the intercept tell us in a simple regression equation? Well, the intercept, or the B0, is the expected value of the DV when the predictor is set to 0. And in a multiple regression case, that is the expected value of the DV when all predictors are set to 0. And so if 0 doesn't make sense for that predictor, remember like GRE scores, who gets a GRE score of 0, right? Well, that's when we would want to center the predictor variable. We don't usually center the DV, recall. But centering the predictor is helpful for interpretation. So we're going to make the mean the 0, and then that will make automatically the y-intercept the mean of the DV. So that's why centering is important, is because it aids in prediction, and this will come up again and again through the stat sequence. Centering is used quite frequently for this purpose, particularly in multi-level modeling, which comes later. So I want you to know what it is and why it's done, and know that it makes the intercept change to the mean of the DV. Most of this segment has to do with the various elements of the ANOVA table. So please keep reviewing this, understand all of those elements and how they relate to one another, and ultimately what goes into the final F test that gives us significance. So know that fraction, know the MS regression over MS residual, and all the factors that play into the sizes of those elements. Okay, so we'll start with the SS regression. And the SS regression gives us an indicator of how well we're predicting the DV. And remember specifically what this means is, are we predicting better than just saying the mean of the DV for any value of X, or the predictor? So remember that we would be doing a very poor job of predicting if we just said the mean of the DV for any value of the predictor. But that would be the best that we could do. Well, SS regression, we want to, basically that's the formula for that, is saying, look, we want to improve on just having to do our best guess, which is the mean of the DV. So if SS regression could talk, it would say, am I doing better than the mean of Y? So that's what we see in the formula. We have, remember, the sum of the squared deviations between our predicted value of the DV and the mean of the DV. And the larger that is, the better, because that is going to comprise the numerator of our F test after we divide it by the numerator df, or degrees of freedom. Remember, the numerator df is k, is equal to k, which is the number of predictors. And think about what happens as k would increase. So as k would increase, we would cut into our SS regression and thereby reducing the numerator of our F formula. And we don't want that. So what we don't want to have is a lot of predictors. We want to be parsimonious and judicious when choosing predictors, because each one uses up a degree of freedom. And so, especially redundant predictors, predictors that are highly correlated with one another, we would want to eliminate those, because we want the SS regression to be very healthy. The SS residual, on the other hand, we don't want that to be large. SS residual is an index of how poorly we're predicting the DV. So remember, it is the sum of the squared deviations between the observed value of the DV and the predicted value. And so we want that to be, those deviations to be as small as possible. Now, if we sum together the SS regression and the SS residual, we will get the total sum of squares. And remember, the total sum of squares is the observed value minus the mean value. Remember that. So the sum of the squared deviations, again, of the observed value minus the mean of Y, always the DV. So those formulas, if you need to review them, they were in the slides from last week. So I highly recommend knowing all of those and understanding conceptually what they're doing as well. Okay, so how do we get the MS regression? Well, we divide the SS regression by K. And so, again, if we have a lot of K, we'll have a smaller MS regression. If we have a smaller number of K, we'll have a larger MS regression. And the goal is to have it larger. MS residual, we divide that by the denominator df, and that is n, total number of points in our data points in our study, minus k, number of predictors, minus 1. So we divide SS residual by n minus k minus 1. And for that, we want lots of n because we want to cut into that MS residual as much as possible because that forms the denominator of our f-test. So the smaller, the better. And remember in our case of 620 n from last week, that's what happened is we were able to cut into the MS residual a lot with that second big sample. Okay, so the SEE is the standard error of the estimate, and conceptually what that is the standard deviation of the distribution of residuals. We don't want that standard deviation to be large because that means that we're not predicting well. We get the SEE by square rooting the MS residual, and we can also get it by the formula of the standard deviation of y multiplied by the square root of 1 minus r squared. So that's the way we can get two ways we can get the SEE, which is kind of cool. So at the mean of a predictor, what is the predicted value of the DV? And that is the mean. So the predicted value of the DV is the mean at the mean of the predictor, and it's that way on any scatter plot. So you would go across on the x-axis to the mean of the predictor, wherever that is. You'd head upwards to the best fitting line, and then head across, and you'll always be at the mean of the DV. Finally, hopefully you know the answer to this by now. When there's no relationship between two variables, what is the expected value of the DV for any predictor value? And that is simply the mean of the DV. As two predictors become increasingly correlated, their B's and their betas shrink. Okay, so all else constant, again, as two predictors increase their overlap with one another, increase their redundancy is another way to say it, then they will predict less unique variance in the DV. So again, the value of adding a predictor only makes sense, I think, if it's not super correlated with the other predictors in your model. You can see this is true in two ways. The first way is by the formula for beta in the two predictor case, and that's in last week's lecture, so go back and look at that formula. It was a little complicated. It had, correlations, so you're plugging in the correlation between the DV and predictor 1, the DV and predictor 2, and then the correlation between the two predictors. And you can see as you hold all else constant in that formula, as the correlation between the predictors rises, then the overall betas and B weights will shrink. So you can also see this in the Venn diagram when in your mind's eye you move the two predictors very close together with one another. Then you can see that the A and the B areas will be shrinking. So look at that again just to see it visually, and then it will make hopefully a lot of sense that way. What is the standardized covariance between X and Y? That is the R. So that is the correlation coefficient. Just keep in mind that the correlation coefficient is a standardized covariance. So it's the covariance divided by the standard deviation of X times the standard deviation of Y. That's an easy way to remember it. Remember that validity is equal to the truthfulness or the accuracy of inferences or conclusions that we're making about our sample, and if our sample findings reflect what's going on in the population. So remember, stat conclusion validity is the truthfulness of inferences that X and Y are statistically related. Internal validity is the truthfulness of inferences that our hypothesized predictor is causing our DV. So there's a causal link there. And finally, external validity is the truthfulness of inferences that the causal link between X and Y it holds or stays significant across various situations, contexts, and people in our sample. And finally, if we center a predictor, what is the y-intercept or the b-naught? And that answer to that is that it is the mean of the dependent or outcome variable. So if we center the predictor, we make its mean 0. And so remember the conceptualization of the y-intercept is the expected value of the dv when the predictor is at 0. And so in that case, when it's centered, the mean is 0, and then when the predictor mean is 0, the expected value of the dv will be the mean of the dv. Recall that statistical power is the probability of detecting an effect in our sample that really exists in the population. I want you to know that definition and also the different factors that impact the size of power. So recall those two curves that we talked about last week. They're here again in this slide in the bottom right. Remember that the blue curve represents the reality under the alternative hypothesis, and the red is the reality under the null hypothesis. And remember, we don't know which reality we're living in. This is just hypothetical. This is for learning to understand the two different possibilities that we have. So remember, the first factor that impacts power is our alpha rate. And remember, our alpha is the type 1 error, and it's the probability of it detecting an effect in our sample that does not exist in the population. And so typically we always make that very tiny. We don't want to commit that error. But remember that we can increase this if the cost of committing a type 2 error is very high. And so in the figure, note what would happen if we moved that alpha over to the right and made it larger. What would happen to power? Power would get larger. Okay, so we would have more of that solid blue space. We would have less of the beta space or the type 2 error, so that would decrease. So take note of that. For the next one is n size, and that one's easy, right? As n increases, power also increases. And especially for finding small effect size, if we have a small effect size in the population and we need to find a tiny effect in our sample, we would need a pretty large sample to do that. Remember, large N gives us the sensitivity to pick up small effect sizes. So we have two factors that impact power that we have control over. We have our alpha, which we can make larger. We just have to justify it when we're turning in the study for publication. And we have our n size, which we sometimes have control over if we have resources to do so. But the effect size in the population is the last thing that affects power, and that we really don't have control over. But if we have a large effect size in the population, a big effect to find, it will be easier to find it. So that means power is increased for our study. If we have this small effect size, we will have diminished power to find that small effect, and we'll need lots of n to detect it. And we'd probably want to raise our alpha as well if we thought it was that small to detect it, and if it was a small but important effect to find. So those are the three things that impact power. Know those, understand what's going on with these curves, pull them apart in your mind's eye, make that effect size larger in the population, and notice what happens to power and to type 2 error, and then squish them together, make the effect very tiny and such that they're overlapping a lot. And note that it's probably going to be more difficult now to detect an effect because power will be diminished. That blue space, there will be less of it in the case where these two curves overlap significantly. So keep working with it, keep thinking about it, don't give up, persist through this so that you can have a good idea of each of these different elements and how they impact the probability of us detecting a true effect that really does exist in the population. I don't think any stats class would be quite complete without at least a passing mention of this phenomenon. And this is important for a couple of reasons. First, conceptually, it's important to understand when this is occurring so that you can make more accurate causal inferences in your daily life. And the second reason is that it just gives us a good idea of how regression works as a whole. In fact, the regression technique itself was named after this phenomenon. So at the most broad level, the reason that this phenomenon occurs is because there are random fluctuations in any variable over time that we cannot predict. And so for reasons that are just pretty simple, and that is that there's never a direct correspondence between an IV and a DV in this life. We can never have this correlation of 1, at least in our research. And so that means that any kind of intervention that we apply that is effective, it will have some effect, but there will also be fluctuations in the DV that we cannot predict, and that's the unexplained variance or the residual. And sometimes that fools us. That residual is pretty insidious sometimes. So here's an example that I thought of. Individuals who are experiencing well-being levels that are way below their personal average are more likely to seek treatment, and that's an intervention that they're applying. However, when they get better, they immediately infer that the intervention helped, usually, when in reality, if they had not sought treatment, they probably would have bounced back to their own personal average of well-being eventually. So we don't know in this case what the effect of the intervention was versus just regression to the mean and coming back to their personal average eventually, automatically anyway, or if it was a combination of both. If it was and usually it's probably that. It's probably the latter. It's probably the intervention had some effect, and then it was also just bouncing back to the mean. Now, let's say a person is experiencing a very traumatic event in their lives that may lower their average well-being over time. That's an intervention in itself. And so if that's the case, then seeking treatment may be very, very important to bring the person's personal average back up over time. So we have a couple of things going on. We have random fluctuations, and then we have interventions that are actually moving people's personal averages. And we don't exactly know what's going on all of the time. So regression to the mean just means that we have these random fluctuations over time. We feel very, very good some days and not so good. And we see this also in job performance. When people are performing on the job, some days they're way above their personal average in job performance, and other days they're below, but they're always coming back to their average. And that is the idea of regression to the mean, is that we're always heading that way. It's like my personal average job performance, I'm always being pulled back to that. Okay, unless there's a really strong intervention that's giving me much better skills or something like that, which we hope for in organizations, right? That's why we apply interventions. But unless we have that, and it's a very effective, powerful intervention, I'm always going to be pulled back to my average performance over time. So over, especially long periods of time, I'm going to have this average over that time period, and I'm always going to be pulled back to that. So another example is kind of along the lines of the illustration we have been using, is this GRE and GPA. So let's say in an ideal world, or actually it wouldn't be the best, but that GRE was the only predictor of GPA. So we have a correlation of 1, which would be, wow, we can predict. However, that's the only thing that affects your graduate school performance, is this test. So motivation doesn't matter. There are no random fluctuations in your performance. It's all this test. So in that case, if you scored way above your personal average on the GRE, then you would really score high on your GPA as well. You would perform very well in graduate school. However, if the correlation is not 1, if you scored super, super high above your average on GRE, then the chances are that's a random fluctuation, and you will regress back to your personal average of the GRE the next time you take the exam. And your personal average would be, in the hypothetical, that you take that GRE an infinite number of times and you take that average. So that would be your personal average, theoretically. Sounds like a very bad idea, I know. All right, so the way this plays out in real life. So I apply an intervention as a practitioner or as a scientist. Or I apply an intervention just in daily life. So let's say I'm at work and I'm a manager and I praise someone's outstanding work. They performed way above their personal average on a certain task. From what I've seen from them in the past, this particular performance is outstanding. So I feel pretty good. I'm like, yeah, they're going to do this next time because I praised them. Well, the next time they perform a similar task, it's not quite as spectacular. So I conclude that my intervention or my praise of their work, let's say I did a public recognition of some kind, it just didn't do the trick. Now, if I was thinking more like a scientist, I would understand that the odds of them repeating an outstanding performance in that sense are very small. And so I would not expect them to perform spectacularly again, but I wouldn't necessarily conclude that I should stop giving people recognition for that reason. Similarly, let's say we have a punishment situation where I'm a parent and my child behaves terribly compared to his personal average. So he behaves extremely poorly, and so I punish him in some way. And parents sometimes obviously punish very harshly. The next day or a few minutes later, the child's performing much better, more in line with his normal pattern of behavior, and I conclude as the parent that my severe and harsh punishment was a very good idea and it worked as intended. In reality, the child was probably just having a very bad day or a very bad moment, and if I would have applied a gentler technique or just left the child alone for a while, he would have come back to his average functioning. So Daniel Kahneman talks about this phenomenon in his book extensively called Thinking Fast and Slow. It's one of my favorite reads. And he basically says that this phenomenon makes us believe that we are punished for being nice and rewarded for being nasty. So I think it's important to just think about what's going on in our lives and take note of when this might be happening, and it might save us from some difficult times in our futures. Regression to the mean was also mentioned in the Lair reading earlier in the quarter, where he says that when we do research, we are often only publishing the extreme ends of a finding. So we're not finding the average effect size in the population. What we're doing is we are capitalizing on these flukes, and if we did the study 3 or 4 times, we would give this RTM phenomenon a chance to occur, and we would zero in or home in on the more accurate finding between 2 variables. So again, this is the idea of replication, how important it is to allow RTM to do its work. So we're not just publishing the extreme ends of a finding, we're publishing again and again. So the ones below the average effect size are getting thrown into the mix, the ones above and the ones that are around the average effect size, so that we're getting more of a distribution of findings to be able to make the kind of inferences that we would like to make as researchers. So that's what RTM is conceptually. So let's turn our attention to this formula before we close out this section. This formula gives us the mathematical reason for why RTM occurs. And so we have the predicted value of the DV there, but it's in z-score terms. So it's a measure of how far away it is from its average, the average of the DV. And then we have the basic correlation between x and y, and then multiply that by whatever x-score we have, so the score on the predictor, but it's in z-score terms, so again it's going to be an index of how far it is away from its mean. So take a look at what happens when the RxY is 0. So again, in absence of any relationship between x and y, what happens? So if we substitute 0 in for that RxY, we see that any value of the predictor score that we stick in there, we're going to have an expected value of 0. That means the mean of the DV, remember, because a z-score is equal to 0. A z-score of 0 is equal to the mean. Okay, so there we have, again, this idea that when we have no relationship between x and y, we are going to be saying that we expect the DV at any value of the predictor to be the mean of the DV. Now, let's go to the other extreme and substitute a 1 in for the RxY. So there's a perfect relationship. That means that we can fully predict the DV with no error, no residual, by knowing the value of the X, or the predictor value. So we stick in a predictor value that's, let's say, a very extreme score. Maybe it's -2, so it's way below its average. So it's an extremely low score. If the RXY is 1, then we will have the same for the expected value of the DV. We'll have a DV expected z-score of -2 as well. So we have no RTM happening in that case. So again, when RXY is 0, when that correlation is 0 between the two variables, we have RTM occurs fully. So there's a full regression to the mean. Any value of X, we're going to get the mean of the DV. When the correlation equals 1, we have no regression to the mean occurring. Now, as so often, as the case that we see in research, the correlation is going to be somewhere between 0 and 1 absolute values. So to the extent that it is low, we'll have RTM occurring where we have an extreme score on the predictor value is going to be muted by that RXY, whatever that is. So if it's 0.2, just substitute that into the formula and see what happens with some fake z-score for the predictor, and notice what happens on the DV. It will be closer to its average. Okay, so that R that is absolute value less than 1 will be cutting into the extreme z-score that we get for the predictor, and we are going to get a predicted value of the DV that is closer to its mean than we had with X being close to its mean. Okay, so extreme score on X will most likely yield a score in Y that is closer to the mean when we have a correlation that is not perfect. So you can see in that formula how it works. Please think about this deeply, understand it conceptually, understand it mathematically, and just know how it may occur. Have some examples of how it may occur in daily life, similar to the ones that I discussed here in this segment. I'm going to use the example here that's given in field on page 281, and it's a study in which we're trying to predict exam performance by using both the extent of the studying that was done for the exam and also exam anxiety. And so we should take note here of the different segments of this Venn diagram. The A and the B portions are the unique variants that are attributable to studying and anxiety respectively. So those are of interest usually to us, and they remember, get smaller as the two predictors become more overlapping. We have the C and D portion, which C plus D, that little piece represents the multicollinearity, or the correlation between the two predictors. That would be like the R12 that we saw last time. And we have one more thing here, and that's the E. And the E is the variance in the DV that is not explained by the predictors in our model. So some have referred to that as error. Sometimes people refer to it as residual, and sometimes people refer to it as unexplained variance. So those are all synonymous, and you might hear all of those throughout your career when we talk about unexplained variability. So we have this complex interrelationship among the variables, and we can see that from the data set. If you run it, there's a data set in Blackboard titled exam anxiety or something like that, and you will see that studying is positively related to exam performance, whereas anxiety is negatively associated, and studying is negatively associated with anxiety. So apparently the more people study, the less anxious they feel. So that's, I guess, a good thing. So we would hope that's the case. So what if we wanted to know the degree to which anxiety and performance are related, and we want to take into account how much studying was done? So in that case, we're looking at trying to figure out that B portion. So the purpose of the next couple of slides is to figure out how to do that, and there are a couple of different ways to do that. So again, we don't want to count the C space twice. That's the rule that we're going by. So it's not like we can just add up the B plus C portion and add up the A plus C portion and, you know, add those all together to get the total variance accounted for in the DV by the predictors. Remember, we can't do that when we have correlated predictors. So we're going to have to go about it another way, and that is we're going to partition the variance in a special way. There are two ways to parse the variance so that we can see the relationship between anxiety and exam performance when accounting for studying being in the model. So I would say that the SR squared is the more important one, so that's the one that I want you to really focus on, but just know that there is a partial, a PR squared as well. So a PR squared is this partial, and the SR is the semi-partial. So most of the time, at least in my field, I would think in yours as well, researchers talk about semi-partials. And semi-partial, the conceptual definition of that is we want to understand the total proportion of variance in exam performance. So in that DV, that is explained only by anxiety. So anxiety only. And what proportion of the total variance. So what that is we have B, the space B, over a denominator B plus C plus A plus E. Okay, so that's the first bullet there. That is equal to the semi-partial. So again, the proportion of total variance in the DV that is attributable only to anxiety, and that is B. It's not C, it's not A, because C and A also share variance with studying. So we're not looking at studying. This is a way to control for variables. So we're controlling for studying right now and looking at anxiety. Other times, I think less often, researchers want to understand how much of the variance in performance does anxiety explain when the effect of studying is removed altogether. So we're going to remove the studying component from exam performance completely. And I'll show you that visually on the next slide, but mathematically the formula again is the B space, so that's the numerator again, so the partial and semi-partial have the same numerator, and so that would be B over the space B plus E. So we're ignoring any variance that is attributable to studying, which is the A and C variance. With partial correlation, we are again attempting to understand a relationship between two variables while accounting for or adjusting for the effects of a third variable. So in this case, our third variable is studying, and the visual here I think is helpful, where Cookie Monster has come and he has eaten away the studying variable completely. So it is gone from our model. It's taken away from the DV, so there's a chunk out of the DV, and also there's a chunk out of the IV. So studying, the effects of studying on the DV and on the other predictor, anxiety, have been completely removed, and so we can just focus on the relationship between anxiety and performance. Okay, so that's the partial correlation, and as you can see in the formula down in the bottom right, the little B section of the diagram is on the numerator, because that's the unique variance, and then the denominator for that is all of the variance in exam performance, the DV, that is not attributable to the control variable, in this case the studying variable. So that would be the B plus E sections. So that forms the denominator. So take note of that denominator. I'll mention it in the next slide when we compare the denominators of the semi-partials and the partials. Also, just a quick note that the partial is an important concept to know, so I want you to just know what it is, but we won't be doing much with partials in this class. However, next class, you'll be doing much more with partials when you're doing path analysis and multivariate. So path analysis is all about partials. It's about understanding the effect of one variable on another, so it's a causal model. And so path analysis is about causality, typically. And so you want to understand one variable's impact on another while parsing out or holding constant the effects of another variable. So that's really important in path analysis, and that's where you'll see partials come up again. At this juncture, it's helpful to remind ourselves of the big picture and why we are doing all of the details that we've been doing up to this point. And that is because we're trying to ascertain the relative importance of different predictors in explaining variance in the DV. And in our research, of course, the DV is often a variable that we care a great deal about. It's some indicator of someone's well-being, or it's an indicator of org effectiveness, for example. And so we really care about what's contributing to that DV and trying to understand what is the most important predictor often. Semi-partials are similar to partials in the sense that they are both dealing with control variables. So a control variable or a covariate is a variable that is correlated with our DV of interest and also our predictors usually, but it's not of primary interest to us in our particular study. So it's not of direct importance. But we include it in our model just to try to clarify or elucidate the relationship between our focal predictor and our DV. So we're trying to get the most accurate picture of that. So an example that I thought of, let's say that you're implementing an intervention of some kind in an organization. So like there's a HR initiative and you're trying to examine its impact on the org's productivity or profitability. And let's say that you have several subunits of the org or regions and you're going to implement the intervention in some regions and not others, and then you'll compare them in terms of their profitability. Now, you know from experience, maybe working in this org, that several factors impact the organization's profitability in any given year. And so you will want to employ some control variables so that you can see more clearly the relationship between the intervention and profitability. You want to isolate that impact. And a lot of times, theoretically, actually, the way to do that is to get the variables that are also impacting, that you think are impacting that DV of interest and include them in your model. Again, do it carefully because you don't want to put a lot of predictors in that model. Remember, we want to keep our K as low as possible, but you'll want to pick the important variables that predict the DV in order to soak up irrelevant variance in that DV, soak up the residual, and you will be able to see more clearly and have more chance of being significant the unique variance that our intervention contributes to the DV. So let me say that again. The more variables that we have that correlate with the DV that can soak up the residual, then we can more clearly see a smaller effect. Let's say our intervention has a small but important effect on the DV. If we include the right control variables, theoretically, we'll be soaking up irrelevant variance in the DV of interest, so the residuals will be reduced, and we'll be able to more clearly see an effect, if there is one, going on with our focal predictor and the DV. So you, as the researcher in this organization, can imagine that there are probably several things that are impacting its profitability, but you believe the most important one will be the previous year's profitability. So what was the trajectory of the org before the intervention was implemented? You believe that will be important in soaking up irrelevance in that DV, that irrelevant variance, so that you can see more clearly the impact, if there is one, of your intervention. So you include the previous year's profitability before the intervention occurs. You include that as a predictor in your model. And then you have the intervention, so whether or not the branch or particular region had the intervention, so that you include that as a predictor in your model. And then you want to see if the intervention has a unique impact on the subsequent year's profitability while controlling for the previous trajectory of the organization, previous profitability performance. So that's the theoretical idea of controls, and we're going to be revisiting that throughout this class because regression gives us this unique and nice ability to be able to parse out variance in that manner. Okay, so back to semi-partials. Conceptually, semi-partials, and please know this, they denote the proportion of total variance in the DV that is uniquely accounted for by a particular predictor. So in this case, we're going to stick with anxiety. And the formula gives us more of a mathematical picture. It's the same numerator as we had with a partial. So it's still the B portion in the Venn diagram. But then on the denominator, we have more elements than we had in the partial. So we have the total variance in the DV, which is denoted by A plus B plus C plus E. So it's the total variance in the DV on that denominator. So as you can see, mathematically, it's always going to be the case that semi-partials are smaller than the partials because we have more elements in the denominator in the semi-partial, and thus making the whole fraction smaller. So the reason that semi-partials are important is because when we are doing hierarchical regression, they are the focus. So hierarchical regression deals exclusively with semi-partials. And what's interesting is that the semi-partial squared give us the amount by which our large R squared will change with the addition of that variable. So let's say we have the semi-partial correlation for anxiety. We square that, and that gives us literally the change in R squared when anxiety is added to the regression model that already contains our covariate in this case, and that is the amount of studying that we do for the exam. So keep that in mind as we move forward, that the semi-partial squared is equal to the change in R squared when that particular variable is added to the equation. In this segment, I want us to just reflect on the differences and similarities among three elements. First is the beta, or the standardized slope. Second is the bivariate R. And third is our semi-partial. And so on the right, you can see the formulas. We've already been introduced to the beta formula, so that should be somewhat familiar. And the SR formula is very similar to that beta, except that it has a slightly different denominator. The numerator is the same. The whole purpose of this is to show you that when we have no correlation among our two predictors, and in this case I'm going to stick with just the two predictor case to make it simple. Later this will apply to three predictors as well, but for now let's just stick with two. So when the correlation between the two predictors equals 0, the beta, the bivariate, and the semi-partial will all be equal. So it's a very simple case, and I really like just the theoretical idea of no multicollinearity between the predictors. In other words, no correlation. So the predictors are orthogonal, independent, uncorrelated. That circumstance is very elegant. It's simple and easy, and I'll show you why here. So just some notation things. Remember that beta y 1.2 just means that that is the beta for predictor 1 when we're controlling for predictor 2. So it's the relationship between our DV and predictor 1 controlling for the presence of predictor 2 in the model. Conversely, if we were looking at the beta for predictor 2, it would be beta and then it would be y2.1 and that would be the relationship between predictor 2 and y controlling for predictor 1. So know that notation. I know this is like a different language, but become familiar. Just take a few minutes to make sure that that makes sense. So we have our formula for the beta, which we've seen before. And for beta 1, we start with the bivariate for predictor 1 and y. Okay, so that's the first element in that formula. If we were doing beta y2, 1, we would start with the bivariate for predictor 2 in that spot, in that first spot in the numerator. So we're going to subtract off the other bivariate, so the bivariate between y and predictor 2, and then we have the multicollinearity term, which is R12, and that is the extent to which our predictors overlap. On the denominator, we have 1 minus the R12, and we're going to square that, that bivariate between predictor 1 and 2. So that's our formula for the beta. And the SR1 is very similar. It has the exact same numerator, but just a different denominator. We square root the term that we would leave as is in the beta. So let's just take a few minutes to understand what happens when we substitute 0 for R12 in the formulas. So if we do that for the beta, we would have the bivariate 1 minus whatever the bivariate is for predictor 2 and y, and then we would have 0. So that whole term would go away. So we would be left on the numerator with just the R1. Similarly, on the bottom, we would have 1 minus and then 0, 0 squared, 0, so we would have just 1. And so we would have R1 divided by 1, which is just R1. And there we have our mathematical proof that when R12 is 0, our beta and our bivariate are the same. And we saw that in the Venn diagram as well visually the other day. So go back to that and tease apart the two predictors, make sure they don't correlate, and just notice that this is the case. All right, so the semi-partial, similarly, we have on the numerator, everything cancels out except the R1. So we would have R1, and then we would have 1 minus 0, and then square root 1 is 1, and we would have R1 over 1, which is just R1. Okay, so there's the mathematical demonstration that we have the equal, all three of these terms are equal to one another when R12 is 0. Okay, so the beta, the bivariate, and the semi-partial are all the same when we have that circumstance. Now, notice when we make the R12 higher. So let's say we keep everything constant in a formula, in the formula, except for R12, we are going to increase that. So as multicollinearity increases, and I've said this before, and you can see that it's true here, that is both the beta and the semi-partial are going to get smaller. And remember visually that was the case as the predictors increasingly overlap. The A and B portions, that's the unique variance contributed by each predictor to the DV they're going to decrease in that case. So, in summary, understand mathematically and conceptually, visually, why it is the case that as predictors come together and become more redundant with one another, why our betas and semi-partials will get smaller. And just big picture, this will help you when you find that your intervention or other things that you may study in the future, like you have 3 or 4 predictors, let's say, and you're wondering why none of the semi-partials are significant, for example, or the beta weights are significant, then you will know to look for the multicollinearity piece. So you'll know let's check and see how redundant these are with each other. And maybe we can eliminate a couple of covariates that we don't need so that maybe we can see the relationship that we're looking for. So again, covariates help us, but not if they're too redundant with one another. Okay, so remember in the previous segment, I mentioned that covariates can help us find the relationship that we're looking for, especially if the effect is a small one that we are trying to find. But the exception to that is that if they're too redundant with one another, and they're too redundant with our focal predictor, then we may not be able to see what we hope to see because the semi-partials are getting smaller. So that's just one thing to keep in mind when we're thinking about what makes the semi-partials and betas significant. Just one more thing before moving on. If the beta is significant, the semi-partial is as well. And if the semi-partial is significant, the beta will be significant. I can't think of a time when one has been significant and one hasn't been. I don't think that means that it's impossible. I just have not seen it. So it's just a good thing, a rule you can keep in mind, that if the beta is significant, then you can pretty much count on the semi-partial to be significant as well. Now it's time to talk about significance testing for B's or betas. And basically it's the same thing. The formulas are a little bit different for B and for beta, but we're going to focus on the formulas for beta. So the significance test for a beta in a regression is just a basic t-test where you have the actual beta itself for a given predictor. In this case, we're going to do beta 1. So beta for predictor 1 over the standard error of beta 1. And the formulas are given below for each of those. We have already seen the one for beta. That one is pretty straightforward, of course. And we want that one to be as large as possible because if we look at the t test, we want that numerator to be nice and healthy and the denominator to not be too large. So again, it's the beta over the error. And we don't want the error to be too much or we won't get a significant t. So look at the very bottom of this slide for the standard error for beta 1. This is the formula. It's a little bit long, but what it has is some elements that are interesting and can help us understand what makes a significant beta. So we have the 1 minus r squared. R squared just is your r squared for your total model. And that is, again, remember, the proportion of total variance in the DV that's explained by this combination of predictors. And then we have the n minus k minus 1 on the bottom of that fraction. And then we have this square-rooted fraction after that, which is 1 over 1 minus r1 squared. That r1 squared is a multicollinearity term. So what it is it's a regression with predictor 1 treated as the DV and regressed on all the other predictors in the model. In this case, let's say there's just 2. We're going to make it easy. So it's just 2 predictors. So it's a regression. It's a regression with predictor 1 treated as the DV and predictor 2 treated as the predictor. Okay, so in the 2 predictor case, this term is the same as R12. So you can consider it just like R12. So that r squared 1, again, is a multicollinearity term. In the 2 predictor case, it's just the same as R12. And notice what happens to that whole formula as we increase that term. So as we increase R12, our standard error for beta becomes larger. So work that out, look at the formula and how it works. Hold everything constant in the formula except for that r1 squared, and it's at the bottom of the second fraction there. And note what happens to the standard error. It's going to inflate. So what multicollinearity does is if 2 predictors are too correlated with one another, and as that increases, it decreases our numerator for the t-test, and it increases our denominator, which it does a double duty in that sense. It overall works to really reduce the probability that we're going to get a significant t for that beta. Okay, so again, we want the numerator to be large, and as R12 increases in the numerator, it's going to reduce that. And then the standard error, we want that to be small, but as R12 increases, we see that standard error increasing. So too much correlation between our predictors. What that does is it does a double duty in the sense that it decreases our numerator for the t-test and increases our denominator. So it does two things, and both of them are not good if our goal is to find significance for our beta weights. Okay, so I want you to know the elements that go into this, understand what goes into, what factors impact the probability of finding significance for a given beta weight. Whenever a regression analysis is run, SPSS gives us something called the adjusted R-squared. This is also referred to as shrunken R-squared in the literature, so just so you know that those two terms refer to the same thing. When we have the situation where the number of our predictors is starting to approach the number of cases in our data set, we have a situation where R-squared becomes artificially inflated. And it is not significant. So it is this weird situation where we have this large R-squared, but it's not significant. And when that happens, we know that the R-squared is kind of lying to us. And so we have adjusted R-squared, which applies a correction that gives us the true R-squared. So this often happens when we're doing applied research and a client asks us to run some analyses on a data set with maybe 60 cases, but there are 45 predictors, and they want us to tell them which of the predictors contributes the most variance in the DV, and so which one is most important. And so you would run them all in, those 45 predictors, and then you would have this situation where we have an artificially inflated R-squared. So we have the adjusted R-squared that shrinks the R-squared back to its proper value so that we can trust what it's saying. So here's the formula for doing that, and there are a couple formulas in the literature at least, but this is the one that is widely used, and I believe it's the one SPSS uses for its correction. I want you to notice the various elements of this formula and understand what happens when we hold all else constant and we increase the n size, and then we hold all else constant and we increase the k, and what happens to the entire formula. So the R-squared in that formula is our observed R-squared, so set that to a value that's easy to calculate, like 0.4 or 0.6. It's totally up to you. 0.6 is kind of large, but it doesn't matter. This is just for learning. So set that to a value, and then when you have that set, plug in a certain k, so k equals 4, for example, and then adjust the n to two different values. So make the n 20 at first, calculate the formula, and then make the n 100, and just see what happens. So take a few minutes at this point, get out a piece of scratch paper, and do some experimenting with this. And what you'll see is that when we increase n, everything else constant in the formula, the observed R-squared and the adjusted R-squared will converge. And that means our observed R-squared is more trustworthy. We don't have to apply a big correction because as n increases, we don't have this issue of our k approaching n. However, as n decreases, the observed R-squared and the adjusted R-squared will diverge. So the observed R-squared is less trustworthy in that case, and we would want to use the adjusted. So notice how that works. So at this point, switch and hold the n constant and increase the K. So set the n size to a certain value like 100. Keep the observed r squared at the same value that you had it. And then do this formula with a k at 4 and then with a k at 80 and watch what happens. And what you'll see is that as k increases, our observed r squared and our adjusted r squared will get further away from each other. And conversely, as k decreases, they will converge. And in that case, the observed r squared is more trustworthy, and it doesn't need a large correction. Remember the idea that when we increase k, we're also lessening the chance that our F statistic will be significant. So all these factors are playing the same role that we've seen before. It's just a similar pattern kind of what's going on. And that is that when we have too many k, we're going to lessen the chance of finding a significant F test, and we will artificially inflate our r squared. So it'll be, again, a large r squared, but it will not be significant, which is odd. Typically, it's not that way, right? The larger the r squared is, the more chance it has to be significant. But with too many k, this can happen, this odd finding. So please know this, understand what's going on here. And if, let's say, I gave you a homework problem or an in-class work problem where there is, 100 cases in your data set, but you have 90 predictors, then you find this very large r squared, what's going on? And you could, explain this idea. Now, if your client does give you this assignment, and you have very few cases in your data set compared to the number of predictors, then is there anything that you can do? Well, if there are a lot of predictors in that data that the client wants you to run, chances are that they are probably redundant with one another. So they probably, at least a few of them, probably correlate highly with each other. And remember, when we have that high redundancy, that multicollinearity, that's not good for our model anyway. So again, we want to be parsimonious with our predictors. So one possible solution that I've put in the bottom of the slide here in the notes is that you can do an exploratory factor analysis, which you'll learn next quarter. And you can... and there's a YouTube little video to show you how to do that in case you're interested. And once you've identified how the variables coalesce into certain factors, so what an exploratory factor analysis does is it takes all of those predictors and it shows you the ones that are correlated highly with one another. And so let's say your 20 predictors are reduced to 4 because certain ones correlate very, very highly with each other, and so then you would have 4 factors. And so basically what you're doing is you're grouping your predictors and averaging them into 1, and so you're taking, like, let's say 5 predictors correlate highly with each other. So you take them and average them together and treat them as one predictor. And so when you do that, you're basically doing a data reduction method, which is great, and you can reduce the number of predictors in your model without, hopefully without making the client concerned in any way. So you're doing a truthful analysis that hopefully will please the people that you need to, who you're doing your work for. So, and it's also a truthful way. It's not altering the data in a way that would be inappropriate in any sense. So this is a data reduction technique. You'll learn more about that next quarter. But what you can do again is you can take 20 predictors and you can correlate them all with one another and see how they coalesce and group into factors. And then take those factors. Hopefully you're going to reduce your 20 predictors into maybe 3 or 4 primary factors and then use those factors as your predictors. And that will provide a much better picture without having an inflated r squared like this. Again, you can also just look at the adjusted R-squared, but a lot of times that's not helpful, as helpful, but it's still a truthful way of looking at your data. There are a couple of ways to do regression, and the first way is the way we've been doing up to now, and that's the simultaneous entry of predictors. And that is that the predictors are entered all at the same time into the regression model, and then we just compare the B weights to understand which of the predictors is contributing the most to the DV. So I think this is the most useful when we have just one control variable and one variable of interest. So just in the two predictor case, for example, we would look at if we had a training workshop to change leadership effectiveness or to increase that, and we would want to control for these participants' pre-workshop levels of leadership effectiveness. So we want to understand, is our intervention working the way that we expect it to when we're controlling for what the participants already had coming in, or their baseline levels. So that's a really simple, elegant analysis, and sometimes that's all you need to have, and so that's useful. The hierarchical method is useful when you have more predictors and you have several control variables. And so at the most basic level, in the hierarchical method, predictors are added into the equation one or more at a time, and they're added in blocks or steps. So each block, and then at each block we assess the incremental change in R-squared. So our research question for this might be something like, does my training workshop explain incremental variance in leadership effectiveness above and beyond at least a couple of controls? First one would be pre-workshop levels, as we had before. And then maybe we want to add years of leadership experience, or gender for whatever reason if we think that's going to matter. So we would put all of these controls in block 1, and we would put the intervention in block 2. So there's a special causal priority or sequencing that's important with hierarchical regression. We want to add first the variables that were pre-existing. So of course gender pre-exists this intervention. So the person's gender existed before the intervention came into play. So we want to put that first in the sequence. Years of experience existed prior in time to the intervention. So we'll put that first in block 1 rather than in block 2. So typically what goes last in the equation is the variables that we're most interested in. So we're going to put the controls in first that we're not as interested in. They're not of our direct focus in the study, and then we're going to enter the ones that we really care about in the second block of the model. Okay, so, and again, all of this is to assess the change in R-squared that we get. If we get a significant bump in R-squared from the variable that we really care about, then we can say with more certainty that this variable contributes more to the DV than these other ones did. Okay, so that's the theory behind hierarchical regression, and there are some issues with it in terms of, Keith brings up some caveats to this. I think the primary problem or challenge that a lot of individuals see with hierarchical regression is that you can get such different results depending on which variables you enter first into the equation. So more on that to come, but that just gives you a little preview. Simultaneous, again, is more simple, and I think it's easier to interpret in some ways. Hierarchical, typically you're working with more predictors, and when you have many predictors, things always get a little bit more complex in that case. So I'm going to insert in here just we're going to do a quick side trail before we actually do a hierarchical analysis. And that is that there are two ways to do a hierarchical regression. The first one is not theory guided at all. So we will let SPSS decide which combination of predictors to use to account for this optimal variance in the DV. So there are different ways to do this, and first there's the backward selection method, where we begin with all of the predictors in the model, and the computer decides which one is not contributing very much variance to the DV, so the least amount of variance, and it kicks that one out. And then it reanalyzes, and it looks at, because the beta weights change when one predictor is kicked out, the beta weights change, and then based on the new beta weights, the computer decides, okay, this next predictor is predicting the least significant amount of variance in the DV, so I'm going to kick that one out, and then it reanalyzes, and it goes through this iterative process until all the terms in the model are significant and they contribute unique variance to the DV. So that's the backward method. The forward method works in reverse. So it begins with no predictors in the model, and the computer looks at how much variance each contributes to the DV, and it selects that one and adds it to the model. And then it reanalyzes and looks at the predictors that are remaining, and it selects the one that adds the most incremental variance or change in R-squared, and then it selects that until there are no more variables to add that would contribute significantly to the model. And finally, stepwise regression is kind of a combination of the backward and forward. It begins with no variables in the model, and the computer selects the predictor that contributes the most variance, and then it selects the next best one that contributes the most unique variance after that. And then if an earlier one becomes insignificant, so it reanalyzes the model, and if that original predictor that it selected becomes insignificant, it kicks that one out, and then it reanalyzes. So it's, again, an iterative process where it's deciding. The second way is theory-guided, where you are the one who's deciding your underlying theory, and you're letting that drive the decision about which predictors to enter in which sequence. So you are the one deciding, as the researcher, which one matters the most, and then you're going to enter that one into the last block. So this is the hierarchical method where you are deciding rather than the computer. So you will see some articles in our field that in our respective fields that use some kind of selection method that is not theory guided, and typically this is done when there are lots of predictors in the model and or many possible predictors for the DV, and so you want to know which ones are the most important. Later, we will talk about the reasons why the theory-guided method is always better. There was an article that came out in 1995, and it was written by Bruce Thompson, and he's an educational psychologist. And he basically in this piece gave 3 rationales for why computers don't do as good a job as humans in deciding the order of entry of predictors in regression. And so the first one, he argued, is that any computer method will inflate type 1 error rate. So basically it makes more predictors look significant in the model than there actually are. And this is because it does this iterative process, and it doesn't adjust for the type 1 error rate at each step of the way. So it's kind of analogous to ANOVA when we're doing many mean comparisons and we have to do a correction so that we're not inflating our type 1 error rate. Related to this concern is a second concern, and that is that partially because of the type 1 error, this method, when we let the computer decide the order of entry, it yields results that aren't replicable in other studies. And so what we have is, if we have the same exact study done multiple times on different samples, these computer methods won't converge across those studies. And so that gives us a kind of a warning sign as to the veracity of the results that we're getting from these analyses. Finally, these methods of computer decisions regarding predictor entry into the model is that they don't identify the best set of a certain number of predictors that explain the most variance in the DV. So to my knowledge, there's no computer program right now that currently exists that allows you to take 30 predictors and tell the computer, I need the 5 best ones that predict the most variance. All of the different entry methods that are available, the backward, the forward entry, the stepwise entries, they do not give you that best set of predictors, and I will show you why in the next segment in a screencast. So just to review, there are 3 different arguments that Thompson has used and that I believe that are still used today. Lots of folks still cite this article to provide rationale for why we should not use these methods. The first is inflating type 1 error, and the second is that the results aren't replicable, which calls into question their accuracy. And finally, it does not identify the best set of predictors that explain the most variance in the DV. So again, if you have 30 predictors, it doesn't tell you the best 5. This is important, big picture again, this is important because clients may ask you to do these methods in order to find the best set of predictors, and I'm giving you rationale that you can explain to those who don't know why these methods don't work and why it's always better for us to enter the predictors in a sequence that is driven by theory and logic rather than letting the computer do that sequence for us. Please see the screencast link in the notes at the bottom of this slide to view a tutorial on how to do a hierarchical regression or a sequential regression. Now note that in the textbook, Keith uses the term sequential to refer to hierarchical methods of predictor entry. So just note that both terms are correct, sequential or hierarchical. The Van Dyck et al. Article on Blackboard provides a nice example for how to illustrate your results in an organized form for consumption by readers. So when you're submitting to a journal, how do you want to display the results of your hierarchical analysis? And so I wanted to give you an illustration of how this has been done in one of the top journals, and so that you could emulate this example and plug in your own data when you are writing up your own results. Okay, so before we go through what the authors did here, I must interject very quickly that there is no set way that I know of to make a table to display your results. I have seen tables in the same journal and across journals, different studies. The authors may perform a similar analysis, but they'll display the results slightly differently. And I'm not sure why this is, but it's not something that we need to really be concerned with. Just know that it happens. You may have noticed this yourself. And I think that a good rule of thumb when you're thinking about writing up your results and how to make the table is to go to a top journal in your field for ideas, and then copy the format of their tables and then replace their numbers with your numbers, and then simply send it in, and if a reviewer has a question or wants you to add or subtract an element of your table, alter some things, then you can do that. But I find that going to a journal is a nice, and looking at how they displayed their results is a nice place to start. And so that's what I'm doing here for you, is I'm giving you an example so that you can have a place to start when putting together a table. And know that you can, again, that there's this practice varies greatly. The exact way that the tables are put together and the way they look can vary dramatically, and that's okay as long as it's readable and it contains all of the things that the readers need to know and that the reviewers are happy with, then it's okay. So table making is partly a science and partly an art, I would say. Okay, so for this study, the authors were looking at error management culture and org performance. And error management culture is simply fostering an environment in a workplace in which errors are freely discussed and communicated, they're planned for, and when they happen, they're dealt with quickly and efficiently. And so training people to behave this way has been very helpful, as the study showed, specifically impacting a couple of DVs. The first one was firm goal achievement, or did the organization meet its objectives? And second, return on assets in the year after the intervention was implemented. So the authors, again, had two DVs, and we can see them across the top of this table. You can see firm goal achievement and return on assets in 1998. Those are the two DVs that they were trying to predict. You can see that they used step 1 and step 2. So they refer to the blocks as steps in their table, as you can see on the far left column. And they had a few predictors, or covariates that they were looking at. The size of the organization they thought would matter for org performance. They thought the industry sector might matter, and I'm not sure how they coded that. I'd have to go back and look, but we'll talk more about coding later anyway. And finally, return on assets in 1997. So here's another case of an example where we want to use as a covariate an indicator of the trajectory of the organization before the intervention was implemented. So this is like a baseline, and you're going to see this as a pattern coming up probably in various studies, and that is people use baseline, the baseline as a covariate in the analysis. So we're parsing out what was the organization like before the intervention happened. So we can imagine return on assets in 1998. That is probably predicted by return on assets in 1997, the previous year. So remember, a covariate is something that's correlated with our DV of interest, and we want to parse out that variance so that we can see the relationship more clearly between our predictor of interest and our outcome. So again, researchers probably didn't, in this investigation, they probably didn't care as much about the B weights of the covariates necessarily, but they just wanted to understand the incremental variance accounted for by their focal variable, which was error management culture. So they do report the B weights, however, for all of the predictors, and that is typical for tables when you submit for publication. The reviewers and the readers will want to see all of your beta weights, so you typically will report those. Note that this table did not report the B weights. That is something that, again, varies across different studies. Some report both, some report just the betas, as you can see here. I think that recently, this study was done in 2005, I think recently there's been a push to include B weights more. I think I mentioned that before last week. So the DF is 3 and 43. So typically when a DF is reported in this way, one number, comma, another number, that means that the DF, the first DF is the numerator DF, which is 3. It looks like we have 3 covariates in block 1, size, industry sector, and return on assets in 97. And then the next DF number is the denominator DF, which is n minus k minus 1. And that makes sense because in the note below the table, we can see that the n was 47. So if we have 47 minus 3 minus 1, that would be 43. So that makes sense. And I'm looking on the first column, by the way, under firm goal achievement, DV. So notice how they did this table. They were able to fit 2 DVs in this one table. That's not always possible, but they did it very well in this case. If they had 3 DVs, they might have to rethink how to do the table unless they could squeeze it all in. So I'm just thinking, giving you kind of an insight into how I'm thinking, because when I'm thinking about, okay, the different possibilities for a table, and your particular study is going to have different kinds of data, different numbers of DV. You may have just 1 DV, so and the different ways that you could lay out a table under those different circumstances. So that's my thinking there. Okay, so we have the change in R squared from block 1, or step 1, which is the covariates, and then we have the jump in R squared due to adding error management culture in the second block or step. And that is 0.30, which is a pretty good number. I mean, that's probably a lot. And so we have the change in F, which is not always reported in every table and every study either, but these authors chose to include it. And then we have the final R squared, which is 0.47. Notice that that is just the change in R squared added together, so we have 0.17 in block 1, 0.30 in block 2, and add them together, and that's 0.47. And so that's a really big effect size, actually. 47%, wow. For firm goal achievement, that's pretty cool. And of course, that's significant. So you can look for yourself. I'm not going to go through the return on assets in 98, but you can see that the pattern is the same, and we have a significant R squared incremental change from the addition of error management culture in the second block, and it's not quite as big as the first one, though. It's looks like it's 0.06, so it's a 6. It looks like a 6% increase rather than a 30% for firm goal achievement. So take a look at this table, understand all of the elements. I would say don't worry so much about the change in F, but the rest of it, know what it is, know what it represents, and look that through and just become very familiar so that these strange things don't seem so foreign. Like, for example, the change in R squared is often denoted as a delta R squared. That just means change in R squared, in case I haven't mentioned it before. So delta, that triangle, R squared just means the change in R squared. A delta F is the change in F, etc. So take the time to become familiar with these different symbols and different notations so that it doesn't seem as foreign or as scary. So that's the goal as we move through this. Let's take an interlude from covering new content and go back and review what we've learned so far. So first, how can the significance of a change in R squared be tested? The way that we would do this is a sequential or hierarchical regression in which we would want to test the R squared change that is due to the addition of one or more predictors that we care about in the model, over and above any effects of the covariates. So we would run that analysis and we would look in the model summary box and we would look for the change in R squared and then determine the significance in the far right column where it says significant F. Now remember that we have to ask SPSS beforehand to give us the change in R squared. It doesn't do that for us by default. So we have to go into, in the linear regression dialog box, we have to select the button statistics and then ask for the R squared, and we also have to ask for the semi-partial correlation. It doesn't give us that automatically. So we can also look at the part, which is a semi-partial correlation, and we can look at its significance, and then we will know that that R squared change is significant as well. If we squared that semi-partial correlation, we obtain the change in R squared. So that's how we would test for the significance of that change. R squared and semi-partial squared are very similar in the sense that they're both effect sizes, but they measure slightly different things. So when we have an R-squared, that just means the proportion of variance explained in a y variable or outcome variable by our predictor variable. So it's for the bivariate case, and remember that's just two variables. The semi-partial squared is a little bit different. It tells us the proportion of total variance in the DV that is explained uniquely by a certain predictor, above and beyond all the other predictors in our model. When predictors are correlated, the semi-partial will always be smaller than the bivariate because, remember, we have that C-space that we need to deal with, and we can't count that twice. And so when we have that overlap, remember the Venn diagram, if you want to go back and look at that, it might be helpful. When those two predictors are coming closer together, they're sharing more variance with one another, and sharing more variance in the DV together, that C-space is increasing. So that means that any variance that they're explaining uniquely in the DV is also diminishing, and that is the semi-partial squared. So again, when the predictors are correlated, our semi-partial will always be smaller than our bivariate effect size, R squared. When the predictors are uncorrelated, when they're pulled apart, then the semi-partial, and they're completely orthogonal or independent, the semi-partial and the bivariate squared are equal. Okay, so they are exactly the same, and you can see that in the Venn diagram as well. All right, so multicollinearity is just a fancy way of saying that variance is shared among our predictor variables, and its effects on the B weights and the betas should be noted. So for both the beta and the B weights, as the variance shared among the predictors increases, we have a diminishing of those beta weights. Similar to the semi-partial squared, it's the same concept. Okay, so as that variance is shared between the predictors, our semi-partials decrease and our B and betas decrease as well. So the standard error of the beta will increase. Remember that formula from a previous segment. We have that formula, and as with the R12 is increasing, the standard error overall is increasing as well. And so that's bad news for our t-test, because our t-test is, remember, the beta over the standard error of beta, and the multicollinearity causes the numerator to decrease, the denominator to increase at the same time. So it's like it's doing a double duty, and it's creating a smaller t statistic. That fraction overall is getting smaller and smaller. Finally, when a correlation is not 1, which value will be smaller? The predicted standardized value of the DV or the standardized value of a predictor score? So any predictor score that we take on our IV, when we multiply it by a value that's less than absolute value 1, then our outcome is going to be closer to 0, closer to its mean. So the answer is that the predicted value of the DV will always be closer to 0 than the observed predictor value, and that's because we're multiplying that observed predictor value by a correlation that is less than 1. And so if this is in any way still murky to you, go back to the RTM slide, the regression to the mean slide, and understand that based on the formula that was given, remember the standardized predicted value of the DV is equal to our correlation coefficient times whatever x value we're seeing in standardized terms, that because of that formula and the way that it works, when the correlation is less than 1, we're always going to have regression back to the mean as a mathematical certainty. So it always will happen. So we could have a very extreme value on the DV, but when we multiply it by that correlation that's less than absolute value 1, we're going to get a predicted value of the DV that's closer to the mean. It's going to be closer to 0 than that observed x value was. Okay, so keep working with it, keep understanding what regression to the mean really means, and conceptually and also mathematically. Moving along, shrunken or adjusted R-squared is basically a correction that we apply to our observed R-squared that is important to do when we have an artificially inflated observed R-squared due to too many predictors in our model. So when we have too many predictors in our model, and as k is approaching n, oftentimes we'll have a very large R-squared, but it won't be significant. So when that circumstance, if that ever happens to you in the future, that should be a red flag to you to know that there are too many predictors in your model and that they need to be reduced. Another hint of this is when our adjusted R-squared and our observed R-squared are very far apart from one another. If that's the case, we should know that our observed R-squared can't be fully trusted, and we should go with the adjusted R-squared, or probably more importantly, delete some of the predictors in our model, or reduce them somehow. Okay, so again, the adjusted R-squared is a correction that is applied when our observed R-squared is artificially inflated due to having too many predictors in our model. We would run a sequential or hierarchical regression rather than a simultaneous one, probably when we have a lot of predictors and we want to group them in some way to understand the incremental variance that is added to the DV along the way. So there's some kind of sequence that we're interested in. So for example, we may have a new therapy technique that we want to test, and we have some demographic variables that we believe will be important to predicting the DV. Let's say the DV is depression or some kind of indicator of a person's functioning. And so we believe that this new therapy will impact that. So we have some covariates that we're interested in. We have a person's age and gender, which we believe will correlate with the DV of interest. So we're going to put them in the first block because they are the ones that, someone's gender and age is something that has been pre-existing way before they ever decided to go to therapy, right? So we're going to put them first in the model because causally they came first. The next thing we may want to do is add a block 2 and put in that block a person's previous counseling experience. So what have they had prior to this new therapy method? And so that is causally comes next. So a person's age and gender is first in the equation, and then we want to see the incremental variance explained by the person's previous counseling and see if that has an effect above and beyond the two covariates. Then let's say in a third block, we want to put in the last block, we want to put in the one that we're most interested in, and that's the new therapy technique. So we're going to put that in the very last step to see its incremental variance explained while accounting for, above and beyond, the effects of all of those covariates. The age and the gender in the first block, and the previous counseling experience in the second block. And then in the third block is the one that we really care about. And we want to see it, the bump that it gives to R-squared. So that would be a perfect case for using hierarchical method rather than a simultaneous method. The simultaneous method is probably best for cases where we have just one predictor of interest and maybe one covariate. So we have, let's say, a covariate of, I don't know, an example comes to mind of the new counseling technique with someone's previous levels of depression. Let's say that's all we cared about. Okay, so we would add those in a simultaneous entry method way, and we would just look at the beta weights to determine if our new therapy explained unique variance and was more important to predicting the DV than was the previous levels of depression the person experienced. So simultaneous entry is simpler. I like it because it's simpler and it's a little bit easier, but the hierarchical gives us more information along the way and gives us those incremental changes in R-squared that we are interested in. For the y-intercept in a multi-predictor model, that just simply denotes the expected value of the DV when all predictors are set to 0. And if those have been centered, it is the expected value of the DV when all the predictors are set to their means, and that will equal the mean of the DV in that case. Finally, type 1 error is the probability of concluding that there is an effect because in our sample we found an effect, but in reality there was not an effect in the population of interest. So we made an error in the sense that we concluded that there was an effect when there really was not. Type 2 error is the opposite. We failed to reject the null hypothesis when in the population the null hypothesis is false. So in that case, we have failed to find an effect that really did exist. Let's switch gears now and talk about the various assumptions in regression. It's important to know what these are. There are 4 or 5 of them. And it's important to know that these assumptions need to be met in our data in order to have the most accurate results that we can. Having said that, we are going to be treading into more murky waters than we have been in up till now. That is because for a lot of these assumptions, there is, first of all, a debate as to how to best resolve them, how to best deal with them. And there is some uncertainty as to testing for them such that we know that they're really occurring versus not occurring. So there's some uncertainty in that aspect. And I'll try to elucidate that better as we go along, further clarify what I mean by some of these things. But just know that I think sometimes we assume that the experts have all agreed on what to do in a certain situation and that that's what we're going to do from now on. And in some cases in our field, that is true. For example, we have bootstrapping methods now that we didn't have before. And almost all the experts agree that bootstrapping is a robust way to deal with data that has, for example, normality assumptions violated. So we do have some of those hard and fast things that we can depend on. However, there are other cases where data and I should say knowledge is still emerging on how to best deal with assumption violations. So measurement error in the predictor variables, I think, is one of those where there's a lot of there's still some uncertainty as to how to deal with it because we know that we have measurement error in all of our variables. We have imperfect measures of our constructs. And so to the extent that that measurement error is impacting the veracity of our results, we really don't know for sure. There is a new paper out that one of my colleagues drew my attention to that I haven't read yet, but it's about this very issue of measurement error and how it impacts, and they argue greatly impacts the inferences we can draw from our regression analyses and also path analyses, which you'll learn next quarter. And this is something that we really can't do much about because our measures are not error-free, and I'm not sure they ever will be. I can't foresee that in the future. So they, I believe, did some Monte Carlo studies and some different simulations and tested different degrees of measurement error and how it impacts the results. And again, I haven't read the study yet, but from what I hear, it can be pretty drastic. And so I don't know what solutions that they give. A lot of times researchers, what I've noticed when writing these types of articles is that they clearly delineate the problem, but they don't have a good solution yet. And maybe you've noticed this when you're reading books about societal problems as well. Typically, we can very clearly articulate problems, and we can articulate solutions way less clearly, and that's fairly normal and just kind of the progression of knowledge. So I could go on and on about this, but suffice it to say that if you feel the uncertainty in this section, that's normal. So I'm going to try to let you know what are the important things to know. And after that, you can go to Field for reference. I highly recommend his chapter called The Beast of Bias, and it is very thorough, and it gives you all kinds of different options to try when assumptions are violated. I'm not going to go over all of those in this lecture because it's just vast, but it's there mainly for your reference in Field. Okay, so the first assumption is that a linear relationship exists between the predictors and the DV, and it's not curvilinear. We're going to be learning how to test for curvilinearity or nonlinearity. That's again, synonymous terms, later in the course. But for now, we just need to be able to visually look at things and see that the relationship is linear. Thankfully, this assumption is very easy to test for. Everybody kind of agrees on its solution, and so it's not a big deal. The second one I've already discussed, this idea of no measurement error in our predictor variables. The third one is homoscedasticity, and we'll talk more about this in a few minutes, but overall, conceptually, this just means that across all values of our predictor, the variability of residuals around those predicted values will be equal. Okay, so the dispersion of residuals around the line will be equal at all levels of the predictor. Residuals will be independent and uncorrelated. Thankfully, this one is easy to test for, and it's easy to resolve as well, due to new data techniques like multi-level modeling. So very thankful for that. Sometimes data is analyzed by groups. So for example, we could have nested data where we have teams and organizations, and a lot of times the members of the same team share different attributes with one another, more so than they share those attributes with members of a different team. So when we have individuals nested within teams or individuals nested within departments in an organization, that is an example of nested data. And nested data often contains correlated errors. Let's say we measure the same individual across time on the same variable, and because we're looking for changes over time. That person would have correlated errors because it's the same individual over time. And so regular OLS regression doesn't work well for time series types of designs, longitudinal designs, and also for nested data, where again we have people nested within teams or groups. So in that case, we would not want to do a regular OLS regression that we're learning in this course. We would want to use a repeated measures ANOVA, or even better, a multi-level modeling technique, or MLM, where we are accounting for the similarities within the group. We're accounting for shared variant, people having shared attributes inside groups, more so than they'd share with people outside their group. So more on that next quarter. You'll learn all about MLM later. But for now, just know that it is an assumption of OLS regression that our residuals be independent or uncorrelated. And finally, residuals are normally distributed. This is another assumption of regression. And if we have categorical data, such as male-female or ethnicity, maybe we have classrooms in an education setting, we would want that outcome to be normally distributed within those categories. And so this is analogous to the Levine's test for an ANOVA. So it's very similar. We have kind of the same patterns as you can see popping up through statistics. We can see similar patterns as we move along. So these are the assumptions of regression. Please know these 5 assumptions, and I will show you how to test for and deal with each one in turn in the upcoming sections. Please refer to the screencast link in the notes below this slide for a tutorial on how to check for the homoscedasticity assumption in the data. Please refer to the screencast link in the notes below this slide for a tutorial on visually checking for residual normality. Please refer to the screencast link in the notes below this slide for a tutorial on checking the distribution of the outcome within different groups for the purpose of comparing the distribution shapes across those groups. So in summary, what are some best practices for dealing with assumption violations? Field talks about bootstrapping. Bootstrapping is, I think, one of the best
tools we have for dealing with assumption violations at this point. And so it is robust, meaning it is accurate even in the face of assumption violations when there is non-normality of residuals and when there's heteroskedasticity. And so bootstrapping is the way to go. We'll talk more about it in this class in future sessions. So other than that, with the linearity assumption violation, we would run a curvilinear regression, which we'll learn about later. And so that assumption is not a big deal. We can always run a quadratic or cubic function and try to deal with that. If the violation is nested data, that means that there are correlated residuals, meaning people are in teams and those teams share different attributes, and so people within teams will make similar residuals, basically, in the data. And so when we have individuals nested within teams, or we have data points from the same person over time, that will also cause correlated residuals. So our regular OLS regression is inappropriate in those cases. In those cases, we want to run either a repeated measures ANOVA or a multi-level modeling analysis, which you'll learn next quarter. Finally, I don't advise transforming the data, although Field gives us instructions to do so for our reference later if needed. I don't advise trimming data or deleting outliers that aren't obvious because bootstrapping can take care of that as well, and plus there is just not the best practice to delete outliers that aren't very, very obvious. So I tend to be more conservative in that respect. Again, bootstrapping takes care of a lot of these problems, and the Windsoring technique I mentioned previously in Field, I think it's on page 198, but it's just a nice way to deal with outliers in a way that's more true to the data.
To wrap up the content for this week, I'd like to talk briefly about dealing with outliers. So we have three different ways of thinking about outliers. The first way of framing them up is this idea of leverage, and that's how far a given case is on a predictor from its mean. And so cases that are very far from their respective means have a potential to have an impact on the regression equation that we wouldn't want. So this is, again, an outlier is something that's having an unfair impact on the data and not giving us a true picture of what's going on in the population. Discrepancy is the distance between the predicted and actual score. So this is like a residual. So we would look at the standardized residuals and maybe make a cutoff point of absolute value 3 and consider that to be an outlier. So discrepancy is another way of thinking about an outlier. And finally, influence. So influence is like the combination of the leverage and the discrepancy. And so this answers the question, how much influence does a given case have on the whole regression model? So these cases, if they're very, very far and they have a lot of influence, they can be pulling that regression line toward themselves. And that is not good because this maybe one case, because it's so far out, is having a disproportionate impact on the regression line. So if we deleted that outlier or used a Windsoring technique, we would lessen its influence on the overall model. So the way to think about influence is the amount that the entire regression equation or these individual beta weights would change if the case was deleted. And so there are a few indices of this. We have Cook's distance index, DFIT, and DF betas, and these are just different ways that researchers have come up with to assess how much influence a particular case is having. So this is just for your reference, and it's just providing the broad framework. I'm going to show you in SPSS how to get these different values and then make decisions about cutoff points for individual cases that are having a disproportionate and inaccurate effect on our results. Please refer to the screencast link in the notes below this slide for a tutorial on dealing with outliers in SPSS. here are the different outlier indicators saved to the data. So each case has a number associated with it on each one of these. And so we can make decisions based on this and determine whether a certain case is going to be an issue or not in our data. And so we have the residual, the standardized residual saved there, and the several distance measures, a leverage measure, and then a DF beta measure. And so all those can be used to determine whether or not to kick a particular case out of the data set. The thing to keep in mind with this is that if we have more than one predictor in our model, which we usually do, we have to run new outlier indicators for that predictor with the DV. So for instance, if we had, if we were interested in airplay predicting the DV together with advertising dollars and attractiveness, we would have to run each one of those separately with the DV. So we would run advertising dollars, correlating that or regressing album sales on that, and then we regress album sales on airplay as well. And we would be saving those outlier indicators along the way on each analysis. So it can get a little bit complex. And with so many indicators, it's hard to know which one to pay most attention to. I would say look at the residuals first, and if you see one that's really large on that, then check the DF betas. That's kind of the route that you can go to kind of make this easier on yourself. But I just wanted to have the full information available to you here so that you can know how to get at these in SPSS. And then look in field for reference as to the cutoff points and the rules of thumb, and he gives quite a detailed analysis of how these outliers work and what to do with them. This concludes the third week's lecture. Thank you so much for the hard work that you're putting into learning this very difficult, complex material. There are so many different nuances and facets to all of this, and I know that it can be challenging. Not the least of which, understanding the three different terms for the same exact concept. I get that, and I just know that I am here for you. The TA is here for you. If you have any questions, please email the TA and then myself if you're still confused, and I'm happy to help in any way that I can. Keep persisting through. Memorize the concepts to memorize. Go over the ANOVA table. I would say that is a big priority, understanding all the different elements in that, and just a plain repetition may be helpful at this point. Saying the words out loud, don't forget that part. Say heteroskedasticity until it's easy. And those are the kind of things that will hopefully bring the material out of the unfamiliar and the murky into the more familiar and comfortable. So thank you very much. I will see you in class.